All right, welcome all to this seminar on programming languages. I'm Peter Schachte. I'm a senior lecturer in the Department of, or the School of Computing and Information Systems at the University of Melbourne. And I'd like to begin by acknowledging the traditional owners of the land on which I live and work, the Wurundjeri people of the Kulin Nation, and pay my respects to their elders, past, present, and emerging. Okay, so I'll be talking about programming languages and the role they play in software reliability and performance. But first, I'll start off by saying why that's important. So as we all know, software is becoming increasingly important in the world. It mediates what we do on a day-to-day basis. And the reason is that software is more flexible than hardware. It's easier to make it do complicated things. And also because humans are expensive and you have to pay them for every hour they work, whereas a computer you pay for once and use it indefinitely. And also humans are inconsistent. They sometimes make mistakes. They're more likely to make mistakes than computers are. So automation is a desirable thing. Meanwhile, computer chips are getting cheaper. Computers are faster and more powerful. And therefore, there's this drive to move more and more stuff onto computers. And that means more and more stuff depends on the reliability and the performance of computers. And at the center of all of this are programming languages on which our software is developed. And so I'll be talking about how programming language research can contribute to reliability and performance of software and the things we use every day. So I'll start off by talking about what I'm not going to be talking about, which is program validation. So the first issue is we develop a piece of software. Is this even the right program that we've developed? Is it going to even solve the problem that even if we develop it perfectly, will it solve the problem that we want it to solve? So Scott Adams here in this old Dilbert cartoon explains the problem pretty well. Sometimes we don't analyze the problem properly, and in this case, didn't even really try to analyze the problem. So I won't talk about this. I'm going to assume that we've solved this problem. This is a problem for software engineering research. So I'll assume that we've built the right program. Now the question is, are we building the program right? So the standard approach to making sure that the program works as intended is to test it. We just run the program lots and lots of times with lots of different inputs and see if the program behaves the way we expected it to behave. So for each set of possible inputs, we say, here's what ought to happen. We run it and see if it does. And we automate all this so we can do it over and over again every time we make a change to the software. But we tend to ignore the observation that was made decades and decades ago by Edsger Dijkstra, which is that program testing can be used to show the presence of bugs, but never to show their absence. In other words, the result of testing may be that we discover some bugs, or it may be that we don't discover some bugs. But if we don't discover some bugs, that doesn't mean they're not there. So testing is not really a reliable way of finding out whether or not our software is correct. And in fact, when we're testing our software, we may not even be testing all the different parts of the software. And even if we are testing every part, every line of the code, that doesn't mean we've tested all the possible inputs. So it may be that we've tested everything, but we haven't tested every possible input, and we may not have tested the case where it actually goes wrong. So the better solution is to formally prove that the program is correct. The problem is that's very difficult and it's very time consuming. So there's software that automates part of this process that can help check that the proof that we're constructing is correct and can even help construct parts of the proof. But that software is notoriously difficult to use, and it's still very time consuming. And even when we're done, we've proved the program correct. Every time you change the program, you need to construct new proofs. So it's really just not tractable. And in fact, it hasn't really been done for any large scale software, just medium scale software is as far as we've gotten. So if we can't do that and testing isn't good enough, then the compromise position is automatic program verification. So the idea there is we add assertions to the program. And this is something programmers are used to doing anyway. So we add assertions to the program to specify what should be the case at various points of the program as it's running. And then we can use, or alternatively, we can use knowledge that we have of the programming language to infer conditions that should hold. There's, certain things should never happen. So for example, we may have an array. We may be indexing that array by some value. Well, we know that the value must lie within the array. And so we don't need to explicitly declare that. The verification system can just know that that should be the case. So program verification is a lot more manageable for programmers, since it really is built on facilities, on assertions that programmers already know how to do. So the usual approach we use to program verification is to essentially look for inputs that will violate the desired condition. In other words, we try to disprove the idea that the program is correct. And if we can show that there's no way to violate that condition, then we've succeeded in verifying the program. And if we find a counterexample, if we manage to find a input that will make the program go wrong, well, that input is very useful to the programmer to debug their code. But the catch is that sometimes we can't do either. Sometimes we can't find a counterexample, but we can't prove that there isn't one. And that's why this is a compromise. So this is all based on the idea of using various theories of program behavior and of typically of the data that the program manipulates to reason about the program behavior. So there are various available tools to support this kind of verification. An old one is called BLAST. There's another one called CPA Checker, and finally Seahorn is a relatively new one. And there are lots more. A different topic is program analysis. So it's often the case that there are many ways to implement a particular part of a program, and some ways are more efficient than others. So it may be possible to optimize a program, to make a program behave the same way, but do it faster. But the best way for optimization to happen is for the compiler to do it, rather than the programmer. So first of all, it's easier for the programmer if he doesn't have to optimize, if the program is just automatically optimized. Another factor is that the compiler may actually do a better job optimizing than a human can, because the compiler, a program, a computer, can do a better job exploring the search space of possibilities. Another reason is that the programmer is more likely to make a mistake in optimizing and fail to consider some case, or for whatever cause, introduce a bug when they're optimizing. Another reason is that programs need to be maintained. And so if we go through the program and make the algorithm more complex in order to make it more optimal, it's likely to be harder to understand and harder to maintain. And finally, as the program is maintained, it will need to be optimized again, or it's likely to need to be optimized again when we make changes. So if the compiler does it, essentially it optimizes every time we compile the program. So the difference between program analysis and verification is that with verification, we're told what we want to be the case. We're told that at this point in the program, this should be true. Whereas with program analysis, we just infer everything we can about the way the program behaves. So without a target, there's a lot more that we can produce, we can infer, but it's often the case that when we're verifying, we need to infer a lot more than just what our desired conclusion is. In any case, once we've succeeded in inferring lots of useful things about the program, there may be lots of different kinds of optimizations that we can perform. The interesting relationship between the two, between verification and analysis, is really both of them are doing the same kind of reasoning. So the same kind of domains of reasoning or theories of behavior of programs is useful for both. So I'll talk about program analysis here, and I'll talk about it in the context of a verification. But again, it kind of doesn't matter whether we're verifying or analyzing. We'll really be doing both in this example. So start off with the bad news. There's really nothing about a program's behavior that can be decided for all programs, which seems like we're kind of out of luck just from the start. But the thing is, for some programs, we can decide interesting properties. So the classic case is termination. It's been well known since before there were any computers that a computer program, that it's not possible to write a program to determine whether or not another program will terminate. But on the other hand, we have cases of certain kinds of programs, for example, we may have a program that's just the instruction halt. Well, it's manifestly obvious that that program will terminate. So sometimes we can prove termination, but we can't always prove termination. And so what we can always do is maybe prove termination. We can decide that a program will terminate, but if we say yes, the program will terminate, that can mean that the program will definitely terminate. But if we say no, that doesn't mean the program will definitely not terminate. It may just be that we can't tell. And so essentially we draw a line in the sand and we say that everything on one line, on one side of the line, we're certain of, and anything on the other side, we're just not sure. And another advantage of that is, what that means is it gives us something that we can say if analysis winds up taking us too long. So, non-termination is one thing, but not terminating within our patience is another thing altogether. The program may terminate, but it may take thousands of years. That's, as far as we're concerned, the same as non-termination. So when we go to analyze the program, it may be that we run out of patience, and so that means we can say, well, it doesn't have the property we wanted it to have, which of course means that we don't know that it does have the property. So here's a little example. Suppose A is a 4-element array. And that means we can index A with A0, A1, A2, all the way up to A3. So those are the valid array indices. So that means down here, when we say A bracket I, because of what we know about the behavior of array indexing, we know that this is invalid unless I is between 0 and 3. So this is a case where we didn't need to write an assertion. Just by what we know of the programming language, we can infer what must be the case. So let's go through establishing that this is indeed the case with this program. So now I should also say, I'm not going to talk a lot about technical issues, but for this, it's kind of important to go through a program. So here's a very simple program. We initialize I to 0. We initialize sum to 0. And then we say, as long as, or until I is equal to 4, or while I is not equal to 4, we let the sum be the sum plus A sub I. So this will add up all the A's, all the elements of A from 0 through 3. Then we increment I by 1, and we'll go back and do it again until I is equal to 4. Okay, so to analyze the program, we can start by saying, well, look, we know that after line 1, after that statement, I is going to be equal to 0. There's no question about that. And likewise, the sum will be equal to 0. But of course, we also still know that I is 0. That hasn't changed. So what I'm writing here is everything we know at a given line, or after a given line is executed. So after the while I not equal 4, well, after that line, or which I suppose really means before we start line 4, what we know is that I is equal to 0 and sum is equal to 0 and I is not equal to 4. But because we know I is equal to 0, that's more precise than I is not equal to 4. So we can just drop that. That implies that I is not equal to 4. Okay, so on to the next line. Now, we don't know anything about A sub I. So it could be anything. So sum was equal to 0 and we added anything to it. That means sum could now be anything. So there's nothing to say about it. So we'll just drop that. On the next line, we say we increment I. So now we know that I is equal to 0. Okay, so that finishes our first pass of analysis, but we have to go again, because at the entry to this loop at line 3, there are actually 2 possible statements that we could have come from. We could have come from line 2, or we could have come from line 5. So here we had that I is equal to 1 and sum is equal to 0. And from line 5, we have I is equal to 1. So we have 2 possibilities. Either I is equal to 0 and I is equal to 0 and sum is equal to 0, or I is equal to 1. So that means now we know that I is between 0 and 1. So this analysis that I'm doing here is an interval analysis. We're remembering, we're inferring an interval around each variable. Okay, so now I have i's between 0 and 1. Well, sum doesn't change I, and we didn't know anything about sum before, so we don't know anything more about it now. So that's the same. When we increment I, now we know that I is between 1 and 2. And then we have to go back around to line 3 again. So now we, hang on, go back. So now we knew that I was between, either I was equal to 0 or is between 1 and 2. That means it's between 0 and 2. And again for the next line, and then increment it again, and now it's between 1 and 3. And right. And so now after line 3, now we know it's between 0 and 3. And again here, and now it's between 1 and 4. And so that means coming into line 3, it's either 0 or between 1 and 4. So it's between 0 and 4. But we also know that it's not equal to 4. After line 3, it has to not be equal to 4. So that means it's between 0 and 3. But the other possibility, which we haven't looked at before because it was never a possibility before, is that I is equal to 4, in which case we exit the loop. So now we wind up with the possibility that I is equal to 4 at line 6. And that's it. That's all that's possible. Because we know now if we take I between 1 and 4 again, and go back and recompute what we got after line 3, we still wind up with between 0 and 3. So this is stable. We've reached a fixed point. So we verified the condition we wanted, which is that I was between 0 and 3 when we get to line 4, in other words, after line 3. So that array indexing is safe. So we verified the condition we want. Likewise, in terms of optimization, we know that when we see a bracket I on line 4, I will be within the range of the array. It's a 4-element array. I is between 0 and 3, so that operation is safe. And that means if our programming language insists that array indexing is checked, it means we can omit the check. We don't need to check if if I is between 0 and 3. And given how simple this loop is, leaving that bit out will actually make a significant performance improvement to that loop. All right, so that's one example. Now let's take on another example. So that's interval analysis. Let's look at this example. It's basically the same, but notice that now well, let's suppose I just made a little mistake when I was editing and I changed my limit to -4. So now I starts out at 0, sum is 0, and now while I say I is equal to -4, we increment I. So what values will I take on line 4? And in fact, will this loop ever terminate? I'm not sure I understand that question. Oh, what's the type? Yes. Okay, so I'm assuming that these are signed integers. I'll actually come back to that in a few minutes. So you might expect that this means that I will always be greater than or equal to 0. This is going to be an infinite loop. It's going to go forever. But in fact, yeah, and that's what most interval analyses will actually conclude for this code. However, it's not really true. So for the most part, if we assume that I is allocated a fixed number of bits, which is the standard thing that in most cases, in most programming languages, I will only have a fixed number of bits, which means that there's a maximum integer. There's a maximum number that we can represent. And if we add 1 to that, then for integer arithmetic, the 2's complement arithmetic, well, even if it's not, yeah, even if it's unsigned, in any case, adding 1 to that will give us the smallest integer. So our arithmetic actually wraps around. So what that means is that the truth about line 4 is that at the time we execute it, I will either be between the smallest possible integer and -4, or it will be between 0 and the maximum possible integer. In other words, it'll be anything except between -3 and -1. So we thought what we had was the number line, the usual, off to -infinity on the left and off to +infinity on the right, and numbers counting up from left to right. But in fact, what we really have is a number circle. And I've drawn it with 0 at the bottom and counting up to the right. So you can imagine we just take that number line and we bend the 2 arrows around so they sort of come together at the top. So I'm pretending here that the possible numbers are the single, well, or there's 10 numbers on this number circle. Of course, it'll actually be a lot more, but this is a lot easier to look at. So this is what the number circle looks like. And what that means is when we had the interval 0 to 3, we thought we had the picture on the top, but what we actually had was a picture on the bottom. But in this case, it doesn't really matter. They behave the same. But in that second example, it does matter. And where we thought the interval we were talking about starts with 0 and goes up, and then starts again at negative infinity and comes up to -4. Actually, what we have is this nice little arc from 0 around to -4. And so that's a nice single contiguous chunk. And you can see that, as I said, it leaves out -1 to -3. Now the interesting part of this is that machine instructions actually work the same way for both signed and unsigned arithmetic. Most machine instructions. There are a few that actually make a difference, but or make a distinction, but most of them don't. And that means the machine instructions don't even know whether the number is signed or unsigned. And if you look at the number circle on the right, that's the one we looked at. The number circle on the left is the unsigned version of the same thing. It's also a number circle. The interesting thing is that the wrap, the place where they wrap around, in both cases is between the biggest integer and the small, or the biggest number and the smallest number, which in our example was at -5. But for the unsigned version, it's at 0. So the wrapping point for unsigned numbers is at the opposite end of the number circle, or the opposite side of the number circle from the wrapping point for unsigned, or for signed. And that means, that makes things tricky if you don't know whether you have signed or unsigned numbers. And so when we were trying to analyze low-level virtual machine LLVM instructions, we found we couldn't really handle them properly without knowing whether they were signed or unsigned. And that's where this idea of wrapped intervals came from. By moving to wrapped intervals, you don't actually need to know whether the numbers are signed or unsigned. And so that gave us this a couple of papers at the Asian Symposium on Programming Languages and Systems, and then in the ACM Transactions on Programming Languages and Systems. Okay, so that's wrapped intervals. Now I'll look at relational analysis, and I'm going to have to speed up a bit here. Sometimes it's not enough to look at just a single variable one at a time, and you need a relational analysis that will allow you to compare multiple variables, or analyze the relationship between multiple variables. So if we assume, this is again about the same program, only this time we're assuming that size is an input variable. And now the comparison to terminate the loop is I less than size. This is probably what you'd actually write. And the analysis we wind up with, if we use our interval analysis on that, is we can just say that 0 is less than or equal to I. We can't infer anything about the relationship between I and size, which is what we need to know in the interval analysis, because we can't relate multiple variables. It's strictly one variable at a time, and we don't know anything about what size is. So the solution is to analyze relationships between variables instead of just variables one at a time. So the relational version of the interval analysis finds or analyzes the differences between variables. It finds upper and lower bounds on the difference between two variables. when we do that analysis, what we can say is that 0 is less than or equal to I. Oh, and by the way, we also analyze bounds on individual variables as well. So we still get that I is less than or 0 is less than or equal to I, but we also get that 0 is less than size minus I. And so that means that we can deduce that 0 is less than or equal to I is less than size, which is what we wanted in order to know that indexing A by I is safe if we know that size is the size of the array. Okay, so the bad news is it turns out that deciding wrapped relational constraints is intractable. It's NP complete, which we published in CADE. I can't even remember what that stands for. But we went on and we sort of gave up on the wrapping part of it and just used the unwrapped version of bounds on differences. So the traditional approach for handling this is to have a n by n matrix where n is the number of variables. And so each element in that matrix, or element ij in that matrix, is the upper bound on vi minus vj, in variable I minus variable j. So that means that the cost of this is now proportional to the square of the number of variables instead of proportional to the number of variables. So it's very much more expensive. But there is a trick we can use, which is, for the most part, particularly where you've got a lot of variables, most of the variables don't have anything to do with one another. They're just not related. And so we call that sparse. So we can take advantage of that sparsity in our representation, and meaning that our operations on this, in order to compute all this, is proportional to the amount of relationships there are rather than the square of the number of variables. But there's a little problem that gets us into trouble, and this is sort of the point of our paper here, that bounds are implied. So, for example, if we know that x minus y is less than or equal to 10 and y minus z is less than or equal to 5, then even if we didn't know anything about x minus z going in, well, we can conclude that x minus z is less than or equal to 15. And so these transitive constraints make the problem significantly more difficult. And the real problem arises because even if you start off with something like initialize I to 0 and initialize sum to 0, then that creates a new constraint that I minus sum is less than or equal to 0, and sum minus I is less than or equal to 0. And then, well, the thing is, sum and I are really completely unrelated. So, no sooner do we conclude these things about sum minus I and I minus sum, do we actually just forget them. We lose them because, well, they're just going to vanish because they can't be maintained. So, so our trick in this paper is to actually not compute them in the first place. We minimize the information that we store rather than maximizing it. And then we just have a trick that we can use to deduce stuff, to imply or to infer relationships when we need to know them. Anyway, so that was a paper in the Static Analysis Symposium in 2016, and a paper we've just had accepted to Transactions on Programming Languages and Systems, still yet to appear, that does all this and also looks at doing the same thing for the sums of variables as well as, or putting bounds on the sums of variables as well as the differences. Okay, so a little bit about representing programs. So for compilers, analyzers, verifiers, whatever we're doing with programs, we need a representation of the program. And so we have what we call the intermediate representation. And the popular approach these days is what's called static single assignment form. And what that means is that instead of having a statement that looks like x becomes x plus 1, we have a statement that looks like x2 becomes x1 plus 1. So we never reassign a variable. We just use a different variable. And then from that point forward in the code, we use variable x2 instead of variable x1. The problem with that is every time you have something like an if then else, afterwards, when the then and the else branch come back together and we continue on in the code, we need what's called a phi node, because we've computed some value for x in one branch and then some different value for x in another branch. We need in the following code to have a single thing that we can go on with. And that's what this phi node does. But the phi nodes really make a mess. If you think about it, it's a weird sort of operation because only one of these two variables could ever possibly exist. One of them comes from the then branch, one of them comes from the else branch. And we can only ever take one of those. So it's a weird sort of operation. And so there's some other programs, other difficulties with SSA, which I'll sort of skip over. But what we observed is that there's a lot of use of horn clauses, which is the basic building block of logic programming, in program verification. So each horn clause gives us a set of conditions, constraints on the variables for a given execution. And therefore, each horn clause it can be separately analyzed, and then it's fairly straightforward to put together the results of those analyses for each clause to give us an analysis for the whole predicate or the whole procedure. So what we proposed is to use horn clauses instead of something like static single assignment form as our intermediate representation for analyzing programs. And so then each clause becomes some true statement about the behavior of the program, allowing us to analyze it. So in our paper, we provided a translation from SSA to horn form. And we showed that this horn clause form, which I call LPVM, sort of like LLVM, but a logic programming version of it. That form solves the problems that we identified with SSA, and it's also simpler than SSA. And so that was published in the journal Theory of sorry. I can't remember what TPLP stands for right now. Anyway, I'll move on. And my last topic will be about programming language design. So some languages are actually better at producing robust programs than others. People often sort of overlook this, but it really is the case that some languages are better than others for writing robust code. So really, the best way to fix a bug is to not have it in the first place. So if you can make it, if your language makes it impossible to express certain sorts of bugs, then those bugs obviously can't happen. That's the best. If you don't have the opportunity to make a mistake, you won't make it. Second best is to detect the bug when the compiler runs, before the program even starts execution. And then when that happens, the compiler will point to the bug, and that usually makes it pretty easy to fix the bug, as opposed to having the program just behave strangely. The third best thing is to abort the program execution and report the bug when it happens. And the worst possible thing is to never report the bug and just do the wrong thing. Accidentally launch a nuclear weapon. That's probably undesirable. So the key to having a system that's actually robust, and the key to developing a large-scale software is software modularity. It has to be the case that the user of the program doesn't need to know how the program was, or that module of the program was implemented. They just need to know their part, how to use it. And on the other hand, the implementer must not need to know exactly how the programmer is going to use it. They need to be able to work independently. So for example, you can imagine somebody wants to print the marks of all the students in a class, and they want to put a little star next to all the students who are in the top half of the class. And so they might do this by using a median function. So they compute the median of all the marks. And it works. It finds the correct median. And they go and print the stars next to all the marks that are above the median. But it turns out that the marks that are being printed out are for the wrong students. And so the way something like that can happen is because to compute the median, probably what happens is you sort the array of marks, and then you find the middle mark. Great, so far so good. But the problem is now you go and use those marks to print out the students' marks, and you've lost the relationship between the marks and the student names. So now you just wind up giving, essentially you wind up giving out the marks in alphabetical order because that's the order you had the students listed in. This could be called spooky action at a distance. I don't think I'm the first person to call it that. The idea is that parts of your program, parts of your data change when you didn't ask them to. Somebody calling a function to find the median of an array doesn't expect the array to be changed. So these days, the standard advice is to make your data immutable whenever possible. So destructive, if you change some structure, like in this case, the array of student marks, that can cause problems, as it did in this example. So having that possibility allows or forces the programmer to be aware of what's going to change when they do things. And the programming language, the compiler, can't help them at all. And what that means is that the code is not modular. You have to understand stuff that's really about the history of the computation, not just this particular call. So usually we think of programming languages as forming a dichotomy. There are declarative languages that tell us what to do, and there are imperative languages that say how to do it, where the programmer specifies how step by step to carry out the computation. So declarative languages make everything immutable, and that gives us lots of nice properties, such as predictability. But declarative languages forbid us from using certain facilities that programmers are used to, like for loops, or looping over things and mutating or modifying variables and so on. And that leaves the question: can we have the best of both worlds? And so my answer to that is yes, I think we can, which is to allow local effects, but disallowing global effects. So I'm suggesting a concept I'm calling interface integrity. The idea is this: that every operation you implement has two interfaces. It has an apparent interface, which is basically what you've said. What are the arguments you're passing in? What are the results you're passing out? And it also has an effective interface, which is actually what is all the information that can be used inside this thing, or is used inside this operation to implement it, and what are all the effects that can be detected later. So we can say that a function or some kind of operation exhibits interface integrity if its apparent and effective interfaces are the same. So in other words, everything that passes into or out of that operation is visible in the call, or at least in the declaration. And that guarantees that we've got modularity. So when you make the call, you see everything that's passing in and everything that's passing out. And so that means we can't mutate data structures. We can't have global variables, since they flow in, since they're used inside, and they can be modified, and so they flow out as well. And any IO that's carried on, any output to files or whatnot, has to be indicated in the arguments somehow. But what it does permit is for local variables to be reassigned, because local variables are local. They're not visible outside, and they are assigned initially when the operation starts, so they don't flow in from outside either. So I'm just going to wrap up very quickly mentioning this. I've been developing with a number of students a new language called Weeba, which is based on the concept of interface integrity. And it's implemented using LPVM. It has some imperative language features like loops, and variables can be reassigned, but it also has declarative language features like strong typing, algebraic types, pattern matching, and value semantics. And it has a few interesting novel features, that every place where you specify a variable can either be a use, where you just leave it alone. It can be an assignment, where the current value is irrelevant and it's just replaced with a new value. And in that case, you precede it with a question mark. Or it can be both, where the old value is used and then updated, where you've preceded it with an exclamation point. I think I better stop there. Yeah, I'm out of time, so I will wrap up there. Anyway, thanks all for coming, and That's all.